In this problem solving session, we'll be solving a problem from chapter 2, which is the stress and strain axial loading. In this problem, said both portions of the rod A, B, and C. This is a rod that has two sections, AB, smaller diameter compared to the other section BC, but BC is longer than AC, made of aluminum, right? For which, but that's both sections are made of aluminum, for which E equals to 70 gigapascal. E here is the modulus of elasticity, or the Young's modulus. Knowing that the magnitude of P is 4 kilonewton, determine the value of Q so that the deflection at A is 0. Corresponding deflection at B. Now for deflection, we know that to be, that's the force times the length divided by the product of the area times its Young modulus, right? So we need to find for each component, right? That's PAB, PBC, right? This is also Q here. Then AB, ABC, E is the same for both because the same material. That's a material constant, a material property, right? So for this problem, let's start with the area of both sections. Now, area of both sections. Area of AB, that is pi d squared, pi d squared over 4, right? This is AB, pi over 4. The diameter, so here we have units in millimeters, and we also have like 4 kilonewton, right? We have in kilonewton. So millimeters, we turn this to meters. Kilonewton, we turn this to newton, right? Just keep things consistent, and so that one don't also have megapascal, we turn to P, right? Now, pi d over 4 multiplied by d squared, right? D squared here with 20 millimeters, so that will be 0 divided by 1000, 0.02 all squared. If we compute that, I will get 314.16 times 10 raised to power minus 6 meters squared. Now for the area of, I don't need to write this out again. So for area of BC, it's pi d squared 4, which is pi over 4. Here we have 60 diameter, which is 0.06 squared, and that will give us 2.8274 times 10 raised to power minus 3 millimeter squared, and that's the area, right? Now if you look at this problem closely, the force in, you already have an arrow, the force in AB, there's a force here, right? P, it's in tension, it's acting positive, and this force here, the force in BC. Now, one mistake people or students typically make is that the force in BC, it's not just Q, but it is Q minus P, because there's an effect, there's a resultant effect from here, right? So here, the force in this member, it's Q minus P. And since it's pointing downwards, that it's in compression, right? So force in member or in the rod AB, it's P, which is in tension, therefore positive. The force in member BC is Q minus P, right, which is compression, and therefore negative, right? Okay, so looking at this, if we are now to find the deflection, let's look for the deflection in a member AB. Now, in this member, it's elongating, because if you have it's stationary, assume here is fixed, right? Assume this, assume this part here is fixed, right? Fixed. If you pull this, you are trying to elongate this member. That's elongation, right? Trying to elongate it. So assuming that's elongation, that's for P, right? Now, the deflection will be the deflection that AB will be PL, that's the length of AB all over the area of AB times its Young modulus. Remember, this is it, P over AB equals to that deflection. Now P, from the question, we were given as 4 Newton. It's here, 4 kilonewton, sorry. Converting that to Newton, that becomes 4 times 10 raised to power minus 4 raised to power 3, not minus 3 Newton. The length is 0.4. Let's cross-check that again. See here, 0.4 in meters, right? So you see the problem. Problem is giving different units. We have millimeters here, we have meters here, right? So point is stay consistent here. Then the area, we've already computed that above 314.16 and 10 raised to the power minus 6. Then the Young's modulus, we have 70, it was 70 gigapascal, which is 70 times 9, 70 times 10 raised to the power 9 Pascal. Now, just to put things in perspective, before we compute that, let's look at the units. Right. Let me see if I can use a different color to make things clear. Let's look at the units. 4 times 10 raised to the power 3. That's for this unit is in it's in Newton. 0.4 now it's in millimeters. Area, it's m squared, that's meter squared. Then from gigapascal to pascal, right? Now if we do some form of dimensional reduction, Newton, that's kilogram per meter squared. That's divided by the time squared. Here is meters, right? Then we have meter squared. Then pascal will be kilogram divided by m dot s squared. Yeah, I think that's right. That's just right. So, of course, okay, let's see meters. Okay, if we put the bracket here, just not to confuse things. So then if we try to divide, right? Simplify this, meter squared divided by s squared, that's time. Then kilogram dot this squared divided by m dot s squared. Right. So if you simplify this, let's see. You can see clearly in this part here that we have some similarities that can cancel out. See, kilogram m squared. They both cancel out, right? Then we have s squared, then we have m squared here too, leaving us with only meters. So our expected value is in meters, which is, of course, is deflection. Deflection is an extension, right? Deflection is an extension. This deflection. Because you have something like this. If you apply a force, expected to move a little. Right here is delta. That's the deflection. So what this tells us is that what we've computed based on the units, our answer should be expressed in meters. So if you compute this, we expect it to be 72.756 times 10 raised to the power minus 6 meters. And that is the deflection for the entire AB, right? That's the deflection of the entire AB. Now, now if we look, okay, well, let's see. So what the question is asking is knowing the determined value of, okay. So it says we've just computed the deflection due to AB, right? That's the deflection due to AB. But that's not exactly what the question is saying. It says the value of Q so that the deflection at A is 0. Now, it says, meaning at this point here, it doesn't move. That's interesting. It doesn't move in the sense that if you consider everything, while you are pulling this force here, there's another force countering it, so that this part, while you're pulling this, you can't force here, there's another force countering, so that this part, there's no movement at this point, right? Okay. So what we've just done is to find the elongation at P. Now, if we move further, because if you're elongating that part, the other part is being shortened, right? It's shortened, that's delta BC. Let me explain that again. If you're applying a force here to pull this, right? I mean, there's enough force here. But if this part doesn't move, what that means is, though you're applying a force here, the force here is not that it's equal, but it's just enough to counter any move or cause any movement at this part. Because if you remember, if you look at this, you have a smaller diameter, you have a larger diameter, different distances. So the forces cannot also be the same, right? But it should just be right enough to prevent any movement at that point. So now for deflection here, it's PL minus, PL, sorry, divided by A, right? Now for this P here, remember it's the force, right? So it's, as we explained previously, it's Q minus P, in the sense that, let me explain that again. Here, there's, for this, you're trying to pull this way, right? But then there's a force that was trying to pull it up. But for it to move anyway by this, there should be, you have to take into account the effect of that force at that end. That's why you're saying Q minus P. Whether Q is greater or less than P, you don't, you just simply write that. The signs will always check out, right? Q minus P times the length of BC divided by the area of BC multiplied by the Young's modulus. And this is delta BC equal to this. Now Q minus P, let's leave that for now. We will know P, but we don't know Q. The length is 0.5 meters, right? Then the area, then this area, we've already computed that area here. Where is that? So, yeah. So that's 2.8274 times 10 raised to power minus 3 times 70 times 10 raised to power 9 Pascal, right? We already know what the units are based on what you had analyzed before. I'll give you so this will be 2.5263 times 10 raised to power minus 9 Q minus P, right? So now in this problem, it says zero deflection at A. It says zero deflection at A. What that means, it's, zero deflection at A. If here doesn't move, if it doesn't move here, despite the force, what that means is that the deflection at this point, that's the deflection in this material is equal to the deflection of this other part. If A, the deflection at zero deflection at A, what that means is B goes to BC, right? Because if you're pulling with a force, here and pulling with another force here, but then there's no movement at this point. What that means is, this is just, what that means that what this moves by, what AB moves by, and how it extends, even if it extends by, peradventure it extends by small, it will be the same this will extend, right? And of course, if it's the same, then technically if this is not moving, this is not moving. If this is moving by 2, this is going down by 2 overall deflection, right? So that's exactly the idea. So AB, delta, or AB, BC, no deflection at A. Now, we already have delta AB, right, which is this one here. So that is 72.756 times 10 raised to the power minus 6 equal to delta BC. Now, if we know that to be delta BC, we can easily equate it to this, right? We can easily equate it to this here. So that is 72.756 times 10 raised to the power 6 minus 6, sorry, equal to 2.5263 times 10 raised to the power minus 9 Q minus P. We already know that P is 4 times 10 raised to the power 3 in newtons. If you don't remember where that came from, that is here, right? That's P. So if we have P here, then you can pause the video and compute what Q is, but you will get Q to be 32.8 times 10 raised to the power 3 Newton, Or if you want it in kilonewtons, it will be 32.8 kilonewtons. So you can see that P is 4 times 3, P is 4 kilonewtons, but this is 32.8 kilonewtons. See, they are different, but overall the deflection is the same because the diameters are also different with different distances. So the value of Q has been computed. Now the second part is the corresponding deflection at B. Now, you see, don't confuse deflection at A, the deflection at AB and BC with how A moves, right? You see, it says, let's assume, sorry, okay, let me make a better drawing. So this is A. If A doesn't move at all, so, there's no movement at this point, right? It's here. But then there's point B here. But B, for it to remain in equilibrium and based on the forces applied, this B has to move a little. Maybe it's compressive right down a little. It has to move downwards a little. That way, the effect of the forces and the distance all remain the same, right? But then we already know that delta AB goes to delta BC. That's what we can get from the problem, right? Basically. So, in essence, delta BC, it has to be deflection with respect to delta, okay, let's look at this again. Delta AB, right? It's simply like the difference between a distance of something at delta A minus delta B, right? If this doesn't move 0, this will be delta B. That will be negative. You get that? Yeah, so the movement at this point will be negative downwards. Similarly, if you look at delta BC, it will be equal to delta B minus delta C. C here is 0, right? Because it's fixed. So we have delta B, right? But it has delta B and it's coming downwards. This C is supposed to be acting with the force acting upward, right? So the same way, you have that here. So delta B minus delta, let's use this one. So this is 0 minus delta B, right? Equals to delta A, and delta AB is 72.756 times 10 raised to the power minus 6 this. So that will give us delta B. So delta B will be negative of that, which is negative 72.756 times 10 raised to the power minus 6 meters. Converting it, you can convert to millimeters to keep it compact, 0.0728 millimeters. And here is the deflection at B. Deflection at A, if you remember, is 0.